folks. Thanks for having me today. So, in this conversation we're going to have today, I'm going to talk about the graph-powered job matcher. And to do this matching, we will be talking about Neo4j and reg and how to get SQL tables to the graphs inside Neo4j. So, just talking a little about me. I have a PhD in computer science. Also leading some data projects in our local Center of Excellence in Artificial Intelligence. I was a professor in the local university and an independent contractor with Xteam, which we work with machine learning, this kind of stuff. So let me move forward. And the first thing I want to talk about today is why hiring still hurts. So I've found some reasons here. So the first one is the ambiguous requirements. So it's usually common to have in the job descriptions and other, stuff like searching and so ambiguities, like some words that are not completely meaning what it should be meaning. One example is like data scientist or data engineering or ML engineering and so on. So sometimes when you describe the job, it's usually ambiguous, like there is no way to identify which position is actually this one. Another problem we may face is the weak signals. So, for instance, inside the resumes, we may have a bunch of skills or buzzwords that actually the candidate has not strong on. They are just mentioned, and it's complicated to separate the ones they are really good from the ones that are just mentioned in the resume. Another challenge is the recency. So when you try to parse a resume, it's hard to identify inside the resume what is recent, like what is being used or being experienced in the last years, what the candidate is not working with anymore. So things like that. Other problems are related to the time zone. So some rules, they are specific for given time zones, and we need to filter the candidates somehow. That is this other silos problem, which is mostly related to the connections between data. So we have data in the ATS, in the coding platforms, LinkedIn, resumes, and it's hard to combine and extract the entities and avoid ambiguities from those multiple sources. And the last one that I've selected to talk about today is the expensive matching. So if we are talking about LLMs, it's not so cheap to use agents and all the LLM infrastructure to match the candidates with the job positions. So the idea here is to try to combine the knowledge graphs we can have using Neo4j with the challenge and try to reduce those problems we face. So, and I've brought some ideas for each of the challenges, like in the case of the ambiguous requirements, we can structurize the data inside the graph in a way that it will be easier to filter by requirements, even when it's mandatory or optional, things like that. About the weak signals, one thing we can do is to try to bring the evidence inside the graphs and try to create the paths with those evidences. So about the recency, one thing we can do is to use a boost function to score more the things the guy worked with or is experienced in a more recent time, more than the ones they usually worked in the past. So continuing about the real world constraints, for instance, time zone, rate range, and things like that, we can add properties for each node regarding those specific requirements, and then filter by them. Talking about the silos, one thing we can try to do to minimize this problem, I would say this is one of the hardest problems we currently have. So to try to combine data from multiple places. And one thing we can do is to use the edges inside the graph to map the entities and try to normalize the fields inside the properties of each node. And even creating some mapping inside the graph. And to do this mapping, we can always use LLMs or related things to extract semantically. So for the last one, the expensive matching, this is the one we are mostly calling about today. So one thing we can do is to, instead of having a multi-agent system with multiple agents, communicating with each other, one thing we can do is try to avoid LLM during the retrieval part and try to have a more deterministic approach using the power of Cypher, the Cypher language inside Neo4j, combined to the vector search this database has native. So yeah, let's move forward. So one thing we need to do when using Neo4j or any graph for job matching is usually to get the data from the relational database and put it in the graph. And it's not standardized or, like a no-brain way to do that. So there are multiple ways to do that. And I'm trying to bring some tips here to improve what you end up having in the graph. So for this specific case, the job matching and HR, we need to take a look on the queries or the ways people usually search for data. What kind of fields they use to search by, what kind of relationships we need to have to get the good results and things like that. So I've tried to synthesize here in this slide all those tips, and let's go one by one. So keep stable keys. One thing that is really important is to keep the primary keys you have in the relational database. Mostly because if you are going to do it in production, it will be not a single or an own step. It will be done frequently, like this migration or this mapping from relational to graph. So every day or every week, you will need to do that. And usually it's not only additions. So you need to update the data as well as it evolves in the relational database. So by keeping the IDs, the primary keys, you ensure this process will not be so hard to do. Another tip I want to bring is to try to put in the edges the business meaning. So not creating only some edges that fulfill the relationships you have between tables. So more than that, try to put the fields inside the edges, since it's a database that supports it, and label them in a way that they will mean something in terms of business. So it's usually one thing we should do to get better queries. So another thing we should do is performance first. So try to add indexes everywhere and unique constraints, use them as much as possible and ensure the data is not duplicated. So yeah, and the last one here, ETL patterns. So the way you do the migration from relational to graph affects the performance for sure. So you should have some patterns when doing that. And I've brought some ideas here. Like there are multiple ways to get the data from a relational database and put in Neo4j. The most common ones are, for instance, exporting the data as a CSV and using load CSV. It's really fast, but it's batch process, so it's not real time. You need to create the file and load this file from time to time, like every day or once a week, things like that. One possible way to do this connection real time is by using APOC combined with JDBC. So with that, you are able to connect from Neo4j directly to your relational database and run a SQL there that will bring data, and you can use this data to create your nodes and edges in the Neo4j database. So another approach, more common for batching as well, or for a single action, is to use ETL tools such as Neo4j import. In this field, we have other kind of tools like orchestration tools such as Airflow. You can create DAGs in Airflow to get data from the relational database and put in the graph inside Neo4j. And the last one I want to bring here is to use Kafka Connect. If you have a Kafka provider, this one may be the best option to get real-time updates because you can connect both databases, like your relational database and Neo4j to this Kafka, and everything that happens in your relational database will be updated in Neo4j. So moving forward, my idea here is to bring the schema. We have one example of schema. So for instance, we have the candidate profile, we have his country or her country, the skills, technical evaluations, the recruitment journey, which will cover all the steps the candidate move it through a given role. So we have a role which represents the job, the company that's offering this role, and the stage inside the recruitment journey the candidate is. So one thing that's important and sometimes hard to do is to separate the must-have from the nice-to-have. And we can do that since it's now in a graph. We can do that by using the relationships properties. So in this example, we can say that a given role requires, as mandatory or not, a given skill, and so on. So, and the essence I've talked about, we can use the same strategy. Like when saying a profile has a skill, we can say what is the level, like senior, junior, and even the last date it was used. Another thing we can do is to use hard filters. Like if it's a must-have, we can use the filter directly in Cypher as a deterministic filter. And if it's a nice-to-have, we can just score more using vector search, for instance, the nice-to-have stuff. One thing that graphs are really good on is explainability, because no matter what is the result or what we are trying to find there, it will use the graph. So we will have a path inside the graph, and this path will bring us from a given node until another node through a path. And this path usually explains a lot about the query. So that's why explainability is really good when using graphs. So now that we know about graphs and how to bring data to graphs, let's talk about RAG, which is retrieval augmented generation. So this is a process we can do with LLMs to improve the response of an LLM. So instead of just asking to the LLM, we can retrieve context and put the context with the question to the LLM to answer. So this is the entire pipeline. It's not so hard to understand. So this is the query here, and if it uses RAG, it will retrieve some documents and put the documents, the textual representation of the documents, as part of the prompting. And when we call the LLM, instead of just bringing the question, we will bring the question and the documents we retrieved. So by doing what we are going to do here, like graph RAG, is all about improving this retrieval step. And this step is really fast because it is not using the LLM yet. So we will use two approaches here, the full text search and the embeddings. So full text search is a search like in Elasticsearch. We can, the search is based on words, basically. And the embeddings, they are more related to vector search. So there are vectors that represent somehow semantically the text inside the nodes. And by combining them, we ensure that we will take the importance of, let's say, proper names, which are basically words, and but also bring the semantic, the meaning of the sentence. So we combine them two inside the Neo4j database, and I mean, my time is really low. So yeah, I'm going to explain here that are other possible ways to represent the data, not only textual data, but also audio, video, and so on. Embeddings are all about representing data, no matter the original model, using a vector of numbers. So with this vector of numbers, we can compare the vectors and bring the most similar entities, in our case, nodes. So what will be the complete pipeline in this case? The first step is to parse the job definition. And during this parse, we will get the nice to have, the must have, the entities, and all the things we can use in the deterministic query. Then we create this deterministic query by this path reasoning. So we create a Cypher query based on what we extracted from the job definition. After that, we do the vector search. And this vector search is basically using the embeddings of the question or of the job definition and the embeddings of the textual representation of the profiles or of what we want to search by. So then we combine them. So usually we have, let's say, an equation like that to combine those multiple things. And in this step, we bust some things. So we put more score depending on specific characteristics we have in the data. We can have this step to explain why we end up with these answers, and also serve it as an API. So for an example, suppose we have this description or this question. looking for a senior engineer with Java and Spring. Nice to have Golang in Brazil, overlap UTC -3 between 1, and the rate is 35 to 50. So the first step is to extract from this sentence some words, and we can do it without using the LLM. We can do it with, standard NLP process. So in this case, we extract the Java, Spring, Golang, the country, and so on. So, and suppose we have this type of text to represent a profile. So basically everything we have in the profile, but as text. So what we are going to do is to create embeddings for all the profiles based on those texts and do the vector search through them. So it's a complete Cypher query in this example, but what I want to bring here is the combination of the vector search in this case with the structurized query. And this query is based on what we extracted from the question. So we are not only doing a reg as a textual retriever, but also using the structure of the graph to retrieve the data. And that is where the powerful of this strategy is. This is one example of the response after the question. And this is a way to create the prompt. So you can, pass the prompt with some placeholder here. And this placeholder will be replaced by what the retrieval requested from the database. So yeah, talking about costs, in this example, I've used Neo4j AutoDB, which starts, the version I've used is free, but if you are going professional, it is 9 cents per hour, around $60 per month. And I've also used the OpenAI API, which is really cheap, like 15 cents for 1 million tokens, which if you have like thousands of queries per day, it will be less than $20 per month. So the average cost for 1,000 questions is around 10 cents in summary. And just to say, that is a way to evaluate the answers, which is by combining LangFuse with RAGAs. So LangFuse is a service system. You can, manage multiple metrics. And RAGAs is a really simple and powerful way to evaluate RAG. So you can put the measurement of RAGAs inside LangFuse and manage how good it's being done there. So that's it from my side. I still have 1 minute for any questions if you have. This is, you can take a picture of this QR code if you want to talk about this more. This is to my LinkedIn. So thank you all for watching and see you there.